So I'll be talking about ACT as a potential Cosmoglobe dataset. So ACT is the Atacama Cosmology telescope. It's a 6-meter telescope located at more than 5,000 meter altitude in the Chashnantur Plateau in the Atacama Desert. So it's one of the best places in the world for this type of observation, together with the South Pole. And then at each location, there's one high-resolution CMB telescope, so ACT and SPT. So these have more than 5 times Planck's resolution and can reach multipoles above 10,000. So there are some differences between being at Atacama and the South Pole. There's more sky available when you're closer to the equator, but you don't get quite as good weather as you have in the South Pole. Aside from those differences, there's a lot in similar between ACT and SPT when it comes to acting as Cosmoglobe datasets. So this plot shows the frequency coverage of ACT. I stole an earlier Cosmoglobe or Beyond Planck plot and added on the frequency bands of ACT here. And you can see that there are 5 frequency bands that correspond roughly to 5 of the Planck frequency bands. There are some gaps. There's nothing at 70 and nothing at 353 gigahertz. But I think we cover a fair share of the Planck frequency area. We don't go beyond that, however. So the main role of ACT is not to extend the frequency range of Planck, but rather to add depth and resolution. But at least we can contribute data both in the synchrotron, CMB, and dust regimes. So this shows the sky coverage and depth of ACT. It's not precisely the current data. It's a small extrapolation, adding 1 more year of observation compared to what we've already mapped, but it should be pretty representative. So the current map here shows the 150 gigahertz depth maps in units of microkelvin arc minute. And you can see that the numbers range typically from as little as 5 to as much as more than 20. And the medium number at this frequency is 17 microkelvin arc minute. At 98 gigahertz, it's 22, and at 220, it's much higher at 51. So these are all numbers for total intensity. The numbers for polarization are roughly the square root of 2 higher. So you can compare these numbers with the Planck median depths, which I got to be about 65, 31, and 43 microkelvin arc minute respectively. So we are deeper than Planck over this whole area that we cover. But of course, Planck covers a lot more of the sky, the remaining 56% of the sky. But that previous picture does not show the whole story. You need to look in multipole space too, because unlike Planck, our noise is very far from white. So the dashed lines here show the square root of the noise spectrum for Planck, with each color being a different frequency. I'm only showing 3 of the bands here because we haven't analyzed the data from the lowest 2 frequency bands of ACT yet. And you can see that with Planck, you have basically a flat noise floor, and then it blows up due to the beam. But when you look at ACT, which are the solid lines, then you see a very different story, where you have this huge blow up of the noise at low L. And then you fall down and reach a bottom, but then the beam starts blowing up immediately. So you don't have this plateau in ACT, at least not in total intensity. If you look to the right, you've got the polarization noise spectra, and there you do actually reach a noise floor before the beam blows up again. I think the thing to take away from this is that, firstly, ACT lets you go roughly 5 times further higher up in multipoles before the beam starts blowing up. But secondly, there's also effectively a lower limit to how far down you can go in ACT, at least to still be competitive with Planck. ACT does have usable data, all the way down here, but it just isn't as usable as the Planck data that already exists. In polarization, this crossover point, which would be where the dashed and solid line of a given curve cross, is a lot lower in L. That's partially because there's a lot less atmosphere in polarization, and partially because Planck has worse performance in polarization. Okay, so for purposes of Cosmoglobe, it's interesting to look at what the time-ordered data of ACT looks like. So we've got currently three dichroic arrays with about 1,500 usable detectors each. These are sampled at 300 to 400 Hertz, but given the speed at which we scan across the sky, which is about 1 degree per second, and our beam size, which is about 1.3 arc minutes fold width half max, it's probably safe to downsample this by 4 times, maybe even a bit more. So the raw data is about 200 terabytes, but with that downsampling, you could get it down to about 50 terabytes. That's still pretty big though. So in the bottom left here, I've got a TOD example. This is not a particularly good weather TOD. It's actually worse than average, but it's the one I happen to pick. And it's still good enough for mapping. So this is what's shown is a single detector. On the x-axis, you've got the time in minutes. And on the y-axis, you have the signal strength in millikelvins. And the red curve is the actual data. And you can see that there's this huge signal here going, by hundreds of millikelvins up and down. And it's azimuth synchronous. You can see that it's got a pattern, and the pattern repeats in sync with azimuth, which I've plotted as the green curve here. But it's not all synchronous. You also got this large trend here on longer timescales. And it's not like the thing exactly repeats either. So it's quite complicated. There are multiple things adding together. You can see there's just some width to the red curve. There's this sort of small jitter. That's small stuff. That's the white noise. That's what you're used to seeing from Planck, for example. And the actual CMB signal, that would be much less than 1 pixel big here. So yeah, that goes to show how much noise there is. And that's why you have so many detectors and integrate for so long. Okay, on the right, we've got the corresponding power spectrum of that red curve. So you can see we've got a white noise floor here. It's got a bit of a tilt at high frequency due to the time constant deconvolution, but mostly it's white above 10 Hertz. In good weather, it could be white all the way down from 2 Hertz or something. But it's important to notice that, at least for people who come from maybe satellite experience, that we've got this enormous increase in power at low frequency. And you can see here at 0.01 Hertz, we have almost 100 million times more power than we have at the white noise floor. So that's important to keep in mind if you don't have experience with ground-based surveys. So what are the difficulties of trying to integrate ACT time-ordered data directly into Cosmoglobe? Well, first we've got a bunch of various types of pickup that needs to be handled. We've got pickup from having the sun and the moon in side lobes. I've shown what's shown here is a sun-centered map on the color scale of minus 500 microkelvin in Q polarization. And you can see that we have significant regions where the pickup from the sun is considerably brighter than 500 microkelvin in Q polarization, and it's not negligible. Some of it's far away, like 90 degrees away, some of it's 60 degrees away, 30 degrees away, 10 degrees away, and so on. Currently, we handle this by simply cutting the most heavily affected data. But that's not optimal, of course. But that would be the easiest thing to do for Cosmoglobe too. There's also ground pickup, which is one of the contributions for azimuth synchronous signal, like what we saw previously. So what you see here is azimuth on the x-axis, and then the width of the band is simply the thickness of an array on the sky. And it's plotted in horizontal coordinates. So here you see that you've got, again, brighter than 500 microkelvin Q polarization pickup. This is quite stable in time, but it may not be completely stable in time. And just trying to jointly map this together with the sky in a sort of ideal maximum likelihood fashion has given disappointing results so far. So currently we filter it, but that's not optimal, and we should try to do better. There's also various pickup that can't be classified as, sun or moon or whatever pickup or ground pickup. It may be magnetic or thermal or something else. It's got messy behavior and we don't understand it. So we filter it. And again, that's something we want to do better with, because you shouldn't do too much filtering if you're trying to make an unbiased map, right? And then there's the large, complicated atmospheric noise that I showed on the previous slide. And importantly, you can't ignore focal plane correlations here. You need to take into account that the nearby detectors see nearby patterns. We've tried mapping with and without that, and it's a huge difference in the residual noise in the map, whether you take these correlations into account or not. In fact, it might be even more complicated. We have recent evidence that modeling left-going versus right-going scans with different noise models might be able to give considerable wins too, which is something we're looking into right now. There's also what we call the little buddies. Those are strong, 100% polarized side lobes that are about half a degree from the main beam. We actually currently handle those pretty well, I think, but it's expensive, and I think it would be even more expensive in a Cosmoglobe framework. You want to avoid having to integrate over many pixels on the sky for every single sample of the TOD, but if you're not careful, that's what you end up having to do. And finally, there's a huge amount of data. I think even though the other things are uglier than that, I still think actually point number 6 is the main problem with the TOD level integration of ACT into Cosmoglobe. Okay, how about the maps then? So the maps are 43,200 by 10,000 pixel maps, with each pixel being half an arc minute in size, which gives 1.6 gigabytes per Stokes component in size. If it were to be expressed as heel pix, that would correspond to n-side 7,036, which isn't supported by typical heel pix tools. So you would end up rounding it up to n-side 8,196. If you do that, then you end up with 3.1 gigabyte per Stokes component. But if you use indexed maps and you share the index between all the different maps, so you only have to store it once, then you can reduce it to 1.3 gigabytes per Stokes component. So for all the data, this amounts to 3 Stokes components times 3 arrays times 2 frequencies per array, which gives you 18 maps or 24 gigabytes if you don't need to split things per season. If you do split the data per season in addition, then it would be at least 5 times as much as that again, or about a bit more than 100 gigabytes in size. So that's big, but it's a lot smaller than the time order data, much, much smaller and much more feasible. If you look in the bottom left corner, you can see what the data looks like on small scales. So here you can see the scale where you can see the actual beam, and you can see individual point sources and clusters. And on these scales, the maps are simple and well-behaved and easy to deal with. On the other hand, if you zoom out and look on the larger scales, then it can look something like this. So this is a map where I applied no filtering, and it's a preliminary map that was not run to full completion, but I think it gives the overall picture of the situation. So you can clearly see that on these scales, you're not dominated by the CMB, you're dominated by other stuff. The other stuff is spatially variable. You got more noise in some regions, less in others. and you've got horizontal striping and other stuff. So on large scales, the maps are messy and noisy and not so easy to deal with. So that's an example of map level difficulties. So in general, the maps are spatially dependent and have spatially dependent stripy noise on large scales. And large here means basically L less than 2000, 3000, or 4000 for the 3 different frequencies we're looking at here in total intensity. And in polarization, those numbers are much lower. So something like L of less than 500 or 700 for the highest frequency. The maps are also contaminated by pickup, both in T and P. It's most noticeable in P actually, because the noise is lower there and the signal is lower there. And you can see an example of this in the bottom plot here. So this is an example map taken at 150 gigahertz. And you can see that it's dominated by these large horizontal stripes, which is definitely not the behavior of the CMB polarization. But you can also see that those stripes are relatively benevolent. They are or benign. They're very large scale, especially horizontally. And it's not so hard to construct a very mild map space filter that cuts away those modes. Another thing to notice here is this region down here, where you can see that suddenly the noise becomes very stripy vertically. This is a region where constant elevation scans results in 0 cross-linking. So that's also something one has to deal with, this type of spatially dependent stripiness, if one wants to deal with this optimally. Okay, so there was a question in the email about when data will be available. So we're currently working on the ACT data release 6, which will be the first release that uses advanced ACT detectors. It will consist of 98, 150, and 220 gigahertz data from 2017 to 2020 inclusive. And overall, that chunk of data is actually 10 times as much data as our previous Cosmology quality data release, DR4. We're aiming to release this hopefully in early 2022, but we'll see. And it will consist of sky and lensing maps and power spectra and cosmological parameters. But there will be no time-ordered data released, just as before. I hope at some point we'll be able to release our whole TOD set to the public, but it does seem doubtful. It's big, hard to host, hard to download, and people require a lot of. It's not easy to use for outsiders, to put it that way. But we'll see. And that will be followed later by a DR7, which adds the 2 low frequencies, 27 and 39 gigahertz, and another season of data, possibly more. Okay. And finally, to summarize the ACT and Cosmoglobe situation, I think ACT's main role in Cosmoglobe would be to greatly expand the multipole range. So aside from overall high resolution, this also gives you a better handle on things like Sunyaev-Sidovich effects from clusters, point sources, and other small-scale things. The ACT time order data is much too large for Commander 3, so I think for the time being we'll have to work with maps. Maybe with Commander 4, as Hans Christian mentioned, you can actually fit in the time order data. The sky coverage is only about 40%. That is quite large, but it still leaves, something like 60% of the sky where you won't have this resolution. And even when you add in SPT, for example, there will still be a lot of the sky that doesn't have high resolution coverage. So I guess one will have to think about how to do that in Cosmoglobe if you have like position-dependent resolution or something. And sadly, both TODs and maps have difficult noise and systematics. But the bright thing is that's mainly restricted to large scales where other sources of data dominate anyway. So actually, one might not have to worry too much about these things.